The title of this segment is a bit like The Lion, the Witch, and the Wardrobe, I'm afraid. But really, the average, the median, and the histogram are three concepts that you have seen in some detail. And you know quite a bit about the relation between the median and the histogram. You know that the median is the halfway point of the areas. In this segment, we're going to sort out the relation between the average and the median and the average and the histogram, just to see how all three are connected to each other. So to start, here is a very simple little list, 2, 3, 3, and 4. And here is its histogram. And before you look at anything else on this page, I'm asking you to please look hard at this picture. See where the bars are. This one's centered at 2. This one is at 3, twice as high as it should be. And the other one's centered at 4 now. The bar is stretching from 1.5 to 2.5. So there is no sense in saying the entries are uniformly distributed within the bar. They absolutely are not. They are just at 2. There is one element at 2, and here there are 2 elements at 3 and another at 4. There is actually nothing going on in the rest of the bar. You could just as well draw sticks at 2, 3, and 4, provided you have the right size of stick in each place. I'm drawing bars because we are eventually going to put smooth curves over graphs like this, and it's useful to get used to looking at them. Just know for now that if your data are whole numbers and you're actually interested in seeing what frequency of each kind there are, then it is conventional, for very good reason that will become clear later on in the course, to center the bars on the values. So this picture is nice and symmetric, and the median and the average are both 3. You can check the average by calculation. The median is 3 by inspection. And so what I've done in the picture below is I have taken this same list and I have simply shifted this 4 out to 7. I've left the others the same. So now I have a new list, 2, 3, 3, and 7. The median is still 3. That's the center right there. The median is still 3. The halfway point of the areas is just there. But the average is larger because the average is now 2 plus 3 plus 3 plus 7 divided by 4. And you can see that had I decided to shift this block along even further, the average would have been even larger, but the median would still have remained 3. We say that the median is unaffected by outliers. An outlier is a data point that lies outside the range of the data, the general range of the data. That does not affect what's going on in the center. And so the median is unchanged by activity at the ends of the data, whether at the high end or at the low end. The average, however, is affected by every single number on the list. So you mess with one number, you are going to mess with the average. This is most visible in datasets of a kind you've seen before. There's your income histogram, the incomes of US adults. This dataset has a histogram that is not symmetric by any means. It is right skewed, and more vividly, we say it has a right-hand tail. You can see this kind of the long wavy thing. And in such a situation, the average is greater than the median. This is exactly the picture that you saw before, where you have the bulk of the observations at one end and then something getting dragged out. So over here you have the Gates and the Ellisons and so on of the world. Well, actually they have been swept in here. They are somewhere out here perhaps. But then here you have the rest of us. And as I recall, the median income was about $27,000. And here are all these people out at 150. They drag the average in their direction, away from the median in their direction. So the average is greater than the median in such a histogram. And this is why when you read newspaper reports about incomes, it is median income that is reported, not average income, because average income is very much influenced by these small number of very high incomes. And so now you're at a point to answer a question that I raised in the intro video to the entire course, which is you take a class and you go to the teacher and you ask, what was the average? Is that a good question to ask? Let's take a look. If you know that a student's test score is above average, then do you know that the student is in the top half of the class? Not necessarily. Suppose you have a distribution that has a shape, and now I'm going to let my mouse do my talking like that. So the class did very well, lots of high scores, but a few people had a bad day and did poorly. Then the distribution of scores would be left skewed. It would have a left-hand tail, a tail heading towards the low scores. So a very small number of students with rather low scores and the bulk of the students with high scores. And in that situation, what would be the relation between the average and the median? You got it. The average would be less than the median in this situation because it's the mirror image of the picture we had for incomes. And so, for example, if the average was 65 and the median was 70, there could be an even bigger difference, but let's just suppose that the average was 65 and the median, which is bigger, is 70, then what about the person who got 67? Well, the person who got 67 is certainly above average, but they are not in the top half of the class. Because to be in the top half of the class, you have to be above median. And so you have to score in the 70s or higher. Now, I'm not being particular here about ties, that is, lots of values being the same, and very particular definitions of medians. It should be clear from the discussion that it is indeed possible to be above average, but not in the top half of the group. And so the average, really, I don't think is that informative when discussing test scores, so I never compute it. And the first time my students realize this, they're very surprised because people in statistics departments are apparently by law supposed to compute averages, not me. If the class is of modest size, I will give the class the stem leaf diagram of the scores. You know that the stem and leaf plot is the most informative thing you can get. And otherwise, I'll give them the median, but I don't compute the average. It doesn't tell them much. And finally, what I'd like to do is I'd like to look at the average and the histogram, because you know a great deal about the median and the histogram. You know that the median is the halfway point of the areas. You start adding up areas from the left-hand side and you stop when you hit 50%. So let's take a look at what the average does. Here's our old friend, 2, 3, 3, and 4. Here's its average. Now, the sensible way to compute the average is to do 2 plus 3 plus 3 plus 4, the whole thing divided by 4. But I have done something a little perverse. I have said, okay, I've got 1, 2. That's 1 times 2. I have 2 3s, and so that total is 2 times 3. And I have a 4. That's 1 times 4. I add all those up and divide by 4. And I will make the move that we made a little while ago, which is divide this 4 through in all the elements of the sum. so that you have 1/4 times 2 plus 2/4 times 3 plus 1/4 times 4. And this calculation is saying that we are computing the average by saying 1/4 of the list is 2, 2/4 are 3, and 1/4 is 4. And you can compute the average by multiplying the distinct values 2, 3, and 4 by their weights, and you will get 3. Now, what was the point of doing this when we can just perfectly fine add 2, 3, 3, and 4, divide by 4, and then be done with it? The point is to notice what happens in this situation where I've dragged the 4 out to the 7. Then you can calculate the average just as we did up here. 1/4 2s plus 2/4 3s and 1/4 7, and you get 3.75. And how is that helpful? Well, it's clear by picture that this histogram is symmetric about the point 3, and it's no surprise that both the median and the average are 3. But it turns out that the average is the balance point of the histogram. And to imagine that, you have to imagine the histogram made out of cardboard, supported on a wire, and you are going to run your pencil along the base of the figure until you get to a point where it balances. And this symmetric figure will balance at its unique center, which is 3. And in that situation, both the median and the average are 3. This figure below, however, is not symmetric. If I hold my pencil at 3, this figure is not going to balance. It is going to tip over this way. And if you're not convinced of that, some of you are saying, well, wait a minute, half the area is to the left of 3. You are quite right. Half the area is to the right of 3. You are quite right. But it still won't balance at 3. It's not just how much area is on either side. It is where that area is located. And the further away you have values, the more those are going to pull the average towards them, and the closer you're going to have to get to those extremes to balance your figure. And so this diagram will balance not at 3, but at 3.75. If you run your picture along here, there's 3, there's 3.5, and right here is 3.75, and that is where this figure is going to balance. Now, I've just told you that, ex cathedra, this is the center of gravity. Those of you who have done some physics will recognize this as the calculation for the center of gravity if you imagine these blocks as weights attached at these distances. So at the distance 2, you have a weight of 1/4. At the distance 3, you have a weight of 2/4 or half. And at the distance 7, you have a weight of another 1/4. Then this is precisely the calculation for the center of gravity. And if you've forgotten that, don't worry about it. Just take my word for it. The average is the balance point of the histogram. And it is in that sense that it is the center of the distribution. So the median picks out the center of the area, the halfway point of the area, and the average picks out the center of gravity.